All right, so this is it recording? All right, process, dynamics, and controls, work for Part C. Okay, so this is kind of looking at the same situation that we had in Part A. So we're doing the Laplace transforms and everything. But now we have a controller using a proportional controller. And then we also have a measuring device. So we'll go ahead and write out what that closed loop is. So what we have going on is we have an input into our system. So that's going to be our Qn. And that is giving out some kind of height. We'll do, so this is kind of the same situation. We'll do kind of the same thing that we did when we looked for H3 the last time. We'll just call this our overall transfer function. And we'll have this be H3. And if you look back at Part A, we found out what H3 was by using the transfer function, which was K tau S plus 1 to the third power. And the way that we got that was just by taking all those block diagrams, and we would multiply Qn by everything that followed afterwards until we got to H3. So we have H3, but we have a set point that we want to reach on our height. H3, we'll call that set point. And let's say that we're not quite there. So what we're going to do is we have our Qn, and then it gives us an H3 in the Laplace domain, but we're not quite there. So we're going to have this go to our measuring device. And that's going to give us some kind of calibrated signal. Oh gosh, I don't have, there we go. Sorry, I have limited view with my phone. So this is going into some kind of measuring device. And it's calibrated to give us back what kind of height we have. This is going to go back here. And what this is going to give is an error. And that error is simply going to be the height of our set point minus the height that we actually have. But since this is in the plus domain, we have 3sp minus h3 times our measurement device. And this is going to go into, also, I call that our transfer function, but that's also just our process. And then this is going to go into our controller. And this is, I think this was either done in homework 1 or homework 2. But that's going to have a value of Kc. So this should, and then finally we get H3. Is that, it's not a super clear image. I apologize for that. I can only do so much with my phone. I need to make my letters bigger. Yes, I can't make this any bigger. All right. So this is our closed loop, and there's an overall formula for our closed loop. Same principle of how we kind of applied Qn, or no, how we made H3 simply equal to K tau S plus 1 cubed times Qn. Even though there's a lot more behind this, I mean, there's a lot more blocks. The overall, we'll apply the same thing to our closed loop and the overall equation, and we will derive this in a minute. But the overall should be H3 equals everything in the forward direction. So GC times G process. And then on bottom is 1 plus everything in the forward direction plus what's on the bottom. So GC times GP times GM times H3 set point. All right, so now to actually derive this. So H3 equals GP times Qn. And we know that Qn is equal to GC times our error. And we know that our error is equal to H3 set point minus H3 times our measurement device. So H3 is equal to GP times GC times H3SP minus H3GN. So then we do a bunch of algebra to get H3. H3 equals GP GC H3SP minus, H3GM GP GC. Do our algebra. H3 1 plus, I'm skipping a few steps, GM GP GC equals GP GC and our set point. Divide this by this. So then H3, like we said, equals GP times GC over 1 plus GM GP GC times HSP. So I'm going to the next page. Go ahead and write here for my own convenience. GC is equal to, that's KC. KC, G process is equal to K tau S plus 1 cubed. And then GM, I think we just set that equal to 1 for sake of convenience. I think that's everything that we need. Okay, so next, take what we just wrote. So H3 KC times K tau S plus 1 raised to the third power 1 plus 1 times KC K tau S plus 1 H3 set point. All right. Take this back. So here is where we will go with this. We're going to apply the final value theorem. which states, and I never learned this in DiffyQ, so this is new to me, but it states that the limit as a function, and we'll just call it h of t to relate it back to our problem, as t goes to infinity, this equals the Laplace transform as s goes to 0. So we'll take this, but we'll want to put this in terms of deviation variables like we did with the other ones. So we're going to do limit as h prime t goes to infinity, and h prime as t goes to infinity, or h prime in this case, is going to be equal to K3. Oh, that should be KC. I don't know where that 3 came from. To the limit as s goes to 0 of our Laplace transformed h, which is going to be s times our transfer function. So Kc Kc our set point, but since we're doing this in terms of deviation variables, our set point is just going to be a unit step of 1, or how do you call that? A unit step. So kind of what I think they're notated as like u of t in DiffyQ. I don't remember exactly how they're notated, but the Laplace transform of that, I think that's u of t, is simply 1 over s. So that's going to be 1 over s in this case, which is very convenient because now this can actually go to 0 because these s's are going to cancel out. So then have s go to 0. C k tau times 0 plus 1 all raised to the third. 1 plus kc times k tau times 0 plus 1 all raised to the third. And that's going to leave us with kc times k over 1 plus kc times k. All right, now to follow up on what we just did. Find through trial and error numerical solution of the differential, the maximum value of the controller gain, which the system becomes unstable. So we're going to have to do that through code. So let me see if you can see it up here in the camera. But we derived, I know it's backwards, it's mirrored, but we derived what our maximum gain could be before it was unstable. So let's show that through a simulation. Down here, I just kind of have some junk code, or not junk code, it's going to be useful, but code from the last one that we just did that I'm going to copy and paste, only because we have a very similar differential equation that we're solving for, and then I want this right here just so I don't mess up any of the syntax, because that's what's killing me and having me make like a video that should be 2 parts into 4 parts long. So let's go ahead and figure out what our new differential equation is going to be. So it's no longer going to be a function of our QNs, only because we have one QN that's going to be at the very top tank, and that's established for what it's going to be. It's going to be 1.12. All these parameters were given, by the way, in the example problem. And the QN will change, although it's going to be a function of it's going to be a function of error, which is going to be a function of set point. So we'll get into that, but we're going to need our set point for our heights. So initial heights at steady state, that's simply going to be an array of, so it's going to be a 3x1, because we have 3 heights, and that's going to be our QNs at steady state divided by B. So like we showed earlier, H3 times B. I mean, B is just how you relate your height to your volumetric flow rate. And then our set point, so H3 set point. Again, everything is in, we're kind of looking at, or we're only looking at the height of the third tank. So our set point is going to be in relation to that. So our initial set point, is just going to be that last value from our initial height. So again, we don't care about this. That should be a function of our set point now. We don't have this going on anymore. Instead, we're going to have an error, and that's going to be equal to our H3SP minus our height. So our set point minus our height. Q1, we're not going to use the long Bernoulli's equation form. We're going to use the simplified B times H1, because like we said, this is linearized. Same deal here, B times H2, B times H3, and then Q1, like we said, that's going to change. So Q1 is going to be equal to our set point plus our controller times the error that we have. So differential of height for tank 1 is going to be the same deal. Q1 minus Q1, or flow rate going in minus flow rate going out. This should not be the same because we don't have any flow going into tank 2 besides Q1. Besides that, I think that should be everything. All right, so now we can solve IVP this thing. So I'm going to take the solve IVP that we did for the last one. We don't have any QNs. Instead, we have our initial set point, and we're going to have a step change of 1. So H3 SP initial plus 1. We don't have a time matrices like we done in the last one. This is going to have to be just a value that we defined. So we'll make that 100. Our initial heights we have defined up here. Redo. All right, I think we can plot this now. So our t-plots, since we don't have an array already, it's going to be np.linspace. Is this recording? Yeah. It gives me a heart attack mid-session anytime I'm not sure if it's recording. 0 to t end. We'll do 500 spaces. Now So now we can plot. So fig equals make subplots. So then fig dot add scatter. We have x equals tplot, y equals res dot solve span of tplot. We need the second values from those. Whoopsie. This gets me every single time. Expected 3 got... No, you got 3. Oh, and p dot full. Shoot. Yeah, so I don't think you need the brackets. There we go. Oh my goodness. I swear syntax is going to be the death of me. Alright, so we can get rid of all of our previous code. So here's our graph. To measure is we can see when it stops getting unstable when the, let's see, so I guess we'll call this difference. So when our, how do I want to do this? So the easy way would just be adjust KC until it just completely goes out of whack like that. But you can do it numeric. Oh shoot, what do we have for KC? I forgot. Oh, 0.3. I need to remember that. You can do it numerically. What you would want to do is you would want to take, so you have to do this in terms of deviation variables. So like we said, we found the maximum value for our gain. So we would need, let's call this difference 1 equals KC times, have we said what K is? No, we haven't. K is equal to 1 over B times K. Is it capital? No, it's not. Divided by 1 plus KC times K. Again, this is when we did the final value theorem and S went to 0. Okay, so that's when our maximum value, so that's our maximum gain. So then we would want to look at, well, I guess we can just look at it here. So 4.7 3.86. We'd want to take the very first, oh no, we'd want to take the very first value and subtract it from our initial value. The problem is I don't think I'll get the syntax. It'd be res of 0 minus res negative 1. No, it wouldn't be that simple. Okay. I guess we'll just play with this, and then when I come back to code the next part, I guess I can show that. But let's do 1.3. Yeah, we see it begin to get more and more unstable. Let's just do 1. It's not good, but it's better than what we had. Yeah, let's see. .536 minus 2. So once we start seeing a big disparity between this final value and this initial value, that's when we know it becomes unstable, because that's what our maximum gain is. Unfortunately, I don't know the syntax to prove it. So I think the question was just at what value of KC does this become unstable? I don't think that we can find an actual value. We can just play around with it and see what happens. Okay, we're not going to spend much more time. We're just going to move on to the next part. But I think that should suffice for the answer. Alrighty. So on to the next part. So derive the expression for the amplitude ratio and phase lag of an open loop transfer function in response to a signed input. Alrighty. Is this recording? Yes. All right. So here's what we have. We have the same closed loop system. You can't see it too well. I apologize. But we have, instead of an H3 set point, we have a sinusoidal input that's going to go through, and the feedback that it's going to give is another sinusoidal response. And that's going to follow the formula of basically the same thing, but with a different amplitude. So we'll call it A bar instead of regular A. And it'll be omega t plus a phase lag, because it takes a certain amount of time to get through. I went ahead and wrote down some important Laplace transformations that we're going to need to know. Can't see them super well. But this is not diffie-q, so I'm not going to spend a ton of time deriving those. But let's go ahead and get started. So we have this response, and it's going through this entire closed loop. So we have A sine omega t, and it's going through. So it's going to be times GC times GP times GM. We said that GM is 1, so we're just going to cancel that out. But we have GC and GP, and we need to Laplace transform this A sine omega t. So that's going to leave us with GC times GP times A omega S squared plus omega squared. All right. The next step that we can take after this is partial fraction expansion. So this is something that we've learned all the way back in Calc 2, and I'm not going to go into all the derivation of it because that would take way too long. But essentially, we can take this formula, or not formula, but this expression, and that's equal to an expansion. And it's not I mean, it would vary from example to example, but it's not defined how long the partial fraction goes on for, but it follows the general formula of AI over S plus BI plus AI plus 1 over S plus BI plus 1 plus AI plus 2 over S BI plus 2, so on and so on. Again, your values for like how many subscript i's you have, that's going to depend on the example. But eventually you're going to get to CS plus D, and C and D would be values that you would, oh gosh, that's blurry. Focus. Be values that you would get by doing this. I know. Don't do this to me now. So we're going to simplify this as GC GP times A omega S squared plus omega squared. And then we're just going to summarize all of this as a summation equals 1 I AI S plus BI, and then plus CS plus D squared. All right, so there are two different routes that we can take from here. I'm going to go ahead and inverse Laplace transform this. So what we'll do is we will Laplace transform both of these. So some constant over S plus B, we see that follows the format of this Laplace transformation. So if we were to inverse Laplace this, we would end up with e raised to the negative bt. Assuming that b is a constant value, those will just die out as time goes on. So when we Laplace transform these, so we'll go ahead and do that. So we'll do Laplace inverse of AI S plus BI plus CS plus D S squared plus omega squared. We'll just go ahead and kill these. So those go away. But then we also see that this CS plus D over S squared plus omega squared follows the format of omega cosine, is it phi? Phi, I think, plus S sine phi over S squared plus omega squared. So that would equal sine omega t plus, and this is where C would equal, what is it, sine phi, I think, and then D would equal omega cosine phi. Okay, so we're going to need to onto these expressions for C and D. We'll come back to those. Just going to flip this over. So we just got those. Now what we can do is like I said, we could go two routes. So now we'll go the other way. So we'll do GC, GP, A, omega squared plus omega squared equals summation I equals 1, AI, S plus BI plus CS plus D S squared plus omega squared. All right. What we want to do here is we want to multiply both sides by S squared plus omega squared. So we'll need to do two steps on this. This is going to be the first one. And then the next will be substituting a value in for S squared. Or not for S squared, but for S. So when we do that, this goes away right here. This goes right here, and then this goes away right here. So we're left with GC, GP, A, omega equals summation I, S plus B, S squared plus omega squared plus CS plus D. Right. And now we want to set S equal to our imaginary number, which is the square root of -1 times omega. S also shows up in our process function, but we'll do that after we do this one. So if we set this equal to I times omega, if we square root this, then we're just left with negative omega squared. So that means this term right here would just go to 0. So all of this would die out. And what we're left with is GC, GP, A, omega equals CS plus D. All right. So now we have to have to input what our GC times GP is. So that's equal to KC, so that's going to be our GC, times K over, and since this is the 3-tank example, it's going to be tau S, which is now omega, or I times omega. I get mixed up with the I's. I like to keep it as I's, but sometimes I mix it up and put J's. That's cubed times A omega. That equals CS plus D. All right. Now for this next step, if we were to factor this out, we would be left with, if we were to factor this guy out, we would be left with a set of imaginary numbers and a set of real numbers. So times A omega equals CS plus D. I think I forgot one thing. It should be equal to alpha. Or not alpha, the new amplitude. We should have that up in front. Which means there should be new amplitude in front of the C's and the D's. I don't know if that's shown clearly. All right. So then we divide. There should be a d omega. What am I missing? Oh, I know what's wrong. That's not supposed to be S. It's supposed to be J omega. J omega. So then if we divide both sides by A omega, we're left with C J omega. Not J, I. That's the correct terminology. I A omega plus D A omega. These omegas cancel out. With I plus R equals I C over A plus let me just pull the A out. Actually, do I want to do that? No, just leave it in there. I C over A plus D A over omega. And through this equation, we can see I is equal to C over A. R is equal to D A omega. Now that we have that, we can substitute in what we found for C and D from when we Laplace transformed this earlier. So C is equal to A sine phi over A. And then we have R that equals amplitude omega cosine phi. Omega cancels out. Okay, so what we can do is we can say that I squared plus R squared is equal to our expression for I squared, which would be new amplitude squared sine phi squared over original amplitude squared plus new amplitude squared cosine phi squared over original amplitude squared. I think it's pretty clear where this is going. So we'll pull out the amplitudes. Equals sine phi squared plus cosine phi squared. This is a trig function, which of course equals 1, so we can just get rid of that. If we were to square root both sides, left with the square root of I squared plus R squared, otherwise known as the absolute value of I plus R, equals our amplitude ratio. So that's an important relation. Then we can also say that I divided by R equals new amplitude sine phi over A over amplitude cosine, or sorry, new amplitude cosine phi over A. So these, of course, cancel out. It's left with sine phi over cosine phi, which is equal to tangent. Is that filling in on the end? Tangent phi. Sorry, I'm left-handed, so anytime that I bring my hand in, it just completely messes up the focus because it covers everything that I write. Focus. Okay, so that leaves us with I over R equals tan phi. And then if we do arctangent, so tan inverse of I over R gives us phi. All right, so these two equations are what we're going to be using in the coding section. All right, so onto these last two parts. So this is generating a Bode diagram and then also generating a plot of the open loop response. So let's get started. I'll write out all the pieces that we need, and then I'll probably have to cut it off and then come back for when I have to write out the script for the plot, because I mess up on those every single time, so I'm going to have to cut out no matter what. Okay, so let's get started. So first of all, we need tau. I don't think we've gotten that yet, and that's very straightforward. Tau is just... that's AC divided by B. We have B defined. Yeah, we already had that defined. All right. Our omega is going to be equal to np dot log space from 2 to 2, or sorry, from -2 to 2, then 1,000 in between. Where do I want to go? So we'll go ahead and say what our process function is, which is it's basically GM, GC, and GP. Yeah, GP. Even though we're defining it as all just GP. GM is 1, so we don't have to worry about that. GC is KC, and then it's multiplied by GP. So that's going to be K divided by tau times S plus 1, and all of this is raised to the third power. So that's GP. Now we'll get IR, or the imaginary number, or like JI plus R. That's going to be equal to, going to be the same thing, but like we said, instead of S, we have, or I mean, we still have S, but we're inputting W times our imaginary number, which is notated as 1J for some reason. I missed when it was just I. So now we can pull out what I and R are, because I, like we said, is all the imaginary part of that. That's np dot imag IR. R is equal to np. Also, I don't know where all of this auto-generated code is coming from. Sometimes it gets it right for what I want to do, but sometimes it doesn't. I'm not sure what's going on with that. So that's our I and that's our R. Our amplitude ratio is, like we defined earlier, that's the absolute value of our two values, which is simply going to be np dot absolute IR. And What else? And then we have the phase, which is that phi or omega value. I'm not exactly sure which one that is. That's going to be np dot unwrap. And then it's going to be np. So like we said, it's the arctangent. And we'll do 2 since that lets us do I over R. And then that's multiplied by our phase lag. Or sorry, it's converted to I guess that converts it to radians. Okay. So we have everything. I think we just need our time and our y values for the closed loop simulation. So that's going to be equal to simulation GP. So we have our lambda function t. We tab that. What in the world? Okay. The function t. So that's going to simply be our sine function 1 times t. And it's going to be equal to 1,000. And then our discretization is going to be equal to 0. R is not defined. Oh, shoot. np.sine, I mean. All right. I think that should be everything. I think that should be all the parameters and relationships that we need to find before we start graphing. So like I said, I'm going to have to cut out so I can actually figure out what that graphing code is supposed to be. But we'll be right back with that.